All right. First, thank you very much for your attendance today, and welcome to this final event and conference of the project SunCoChem. Well, my name is Maria Navarro, and as you know, I'm the of SunCoChem. Just a few data about the project for the ones that are not so familiar with it. SunCoChem is an European project whose main objective has been the development of a photoelectrocatalytic reactor that takes the sunlight and the industrial CO2 to produce oxo products or green chemicals. Okay, with a budget of almost 7 million euros. We started on the 1st of May of 2020, and we have been working collaboratively during 4 years and a half. All right, and it's as you know, and the results achieved during these 4 years and a half has been thanks to the effort and seamless cooperation of 14 partners. You can see here the names of all of it, belonging to 8 different European countries. It has been for me a pleasure to get to know all of you because, we have really worked very hard, and you will see in the coming presentations all results produced. Okay, let me start offering you a brief overview for the agenda today. During the opening plenary, we will have 2 presentations. So without further ado, we will start with the first presentation of the opening plenary. Let's welcome Adriana Nogalska. Adriana is the SunCoChem Scientific Coordinator and Head of Hydrogen Technologies. A bachelor's degree in cosmetic chemistry and a master's degree in chemical materials from the Adam Mickiewicz University in Poland, a doctorate cum laude in nanoscience, materials and chemical engineering from the University Rovira and Virgili in Spain. Specialized in electrical engineering, she is focusing right now on the field of hydrogen production. So, Adriana, ready when you are.
Thank you, Maria, for your kind introduction. Welcome everybody to the last event of SunCoChem project. I'm Adriana Nogalska. I had the pleasure to be a scientific coordinator of the project during last year. I will give you an overview. I will give you an overview of the results achieved through the project, which then be further explained in more detail in next sessions. Let's start with the motivation for our project. We believe that the decarbonization of chemical industry is the first step to achieve a goal set by European Union to become carbon neutral by 2050. The chemical industry is emitting 30 gigatons of CO2 yearly. However, we cannot completely get rid of carbon because it's a basic building element of many chemical compounds. For this reason, we should move towards defossilization because 95% of the chemicals is based on fossil fuels. The idea is to use carbon from above the ground and also to recycle it. In SunCoChem project, we developed a photoelectrocatalytic reactor that can manufacture oxo products from CO2, water, and sunlight, integrating in one reactor the CO2 capture and conversion. We got inspiration from from nature, from the process of photosynthesis, where the plants are using water, CO2, and solar energy to produce new products, in this case sugar and oxygen. Similarly, in SunCoChem project, we are using the industrial emissions from Dow to get the CO2, water, and sun energy to convert it into oxo products, passing through a synthesis of a syngas, which is composed of carbon monoxide and hydrogen. The oxo products of our interest were 3. It was limoxal, valeraldehyde, and glycolic acid. The main objectives of our projects was to maintain performance of our device during a long-term operation, to obtain relatively high sunlight to CO conversion, and of course to decrease the CO2 emissions of the production for the OXO products in comparison to the actual routes that are using the fossil fuels. Okay, the project was divided in 4 phases. First, we start with the development and synthesis of the materials, which were the catalysts, the electrodes, and membranes. Then we integrated them in a single cell and optimized them. Then we moved to the upscale of the materials and the validation of the final device. We also had a 4th phase that was more transversal one, connected to socioeconomic and environmental impact assessment. We started from a CO2 concentration, where we had to separate the CO2 from the gas mixture from the output of Dow. For this purpose, we developed a polymeric porous membrane, which was incorporating ionic liquid that improved the affinity of the material to capture CO2. We obtained very good results of the CO2 solubility and permeability of these materials, what allow us to apply for a European patent. Once we have the CO2 concentrated, then we move to the photoelectrochemical part. So in the, I don't know, is there a pointer? Well, in the center of the cell, we have a bipolar membrane. The membrane is divided in two parts. We have a cation exchange layer and anion exchange layer, and in between them we have a catalyst that is used to dissociate water. The water is dissociated to hydroxide ions and protons. The hydroxide ions are oxidized on the photoanode made out of bismuth vanadate to oxygen, while proton, together with CO2, is being reduced to hydrogen and CO, respectively, on the cathode. For the cathode material, we use copper oxide tin oxide based semiconductor and coordinated to it rhenium-based co-catalyst. This system was tested at the TRL3 level at a single cell scale with 100 square centimeters of active area. And during the 2 hours of operation, we were able to obtain a stable syngas production with a CO2 conversion of around 30% and sun-to-fuel efficiency of around 4%. Then from the single cell, we moved to the bigger scale. We had a reactor that was designed and constructed by EasyTech. It was installed in EURECAD premises and tested. First, I will show you the results that we obtained from testing of a single string, which was composed of 5 cells that sums up to 500 square centimeter of active area. After many months of experiments, we achieved a stable syngas production during 27 hours and also pretty stable current. And we moved to the testing of the entire reactor using a sun simulator that was provided by Solaronics. Additionally to the photoanodes, we also used PV panels that were also specially designed for this reactor in order to supply more energy to the, but always sun energy, to the reactor. We tested it at a 2000 square centimeter scale, which is up to our knowledge the biggest photoelectrocatalytic reactor that can convert CO2. And however, we saw that the reactor was mainly producing hydrogen. As I mentioned before, when we were testing the single cell, it took us 10 months. So we assumed that the hydrogen production, only hydrogen production, is due to a slight deactivation of the catalyst, and also the catalyst might lost the selectivity. Besides, we also encounter many challenges on the way, connected to the reactor itself, to the fluidodynamics, of the electrolytes and of the gas part. Then we were optimizing it using both simulations and experimental testing, and all of these challenges were then answered in the final pilot. Okay. Once we produced the syngas, then we moved to the oxo product synthesis. Through the hydroformylation reaction of limonen, we can obtain lime oxide. It's the exemplary product that we used in validation of the pilot. This is a building block that is applied as a perfuming agent in a personal and home care produced by IFF. And based on our LCA studies, we saw that the SunCoChem system can reduce CO2 emissions up to 30% in a comparison to the actual route that is based on fossil fuels. We also performed social impact studies on two groups. The first group was industrial experts. They were very positive with our process, and they were willing to apply the process in their production. And the second group were the consumers, which were also very positive. However, they were much more critical. They were standing that they are willing to buy the products that are made out of recycled CO2, but they must be assured that they are really adding something to the climate change mitigation, and also that the products have a competitive price. Okay, for the pilot plant testing at TRL4, we also have a first pilot that is integrating the three processes, which is the CO2 separation, conversion, and the oxo products synthesis. We also added a purification step for the product through distillation. This pilot was designed and constructed by EasyTech, and it's now installed in EURECAT premises at Amposta. I would love to show you some results, however, they are still under development. We are going to publish them to the scientific community in next weeks. Through the standardization activities, we were able to publish CEN workshop agreement on the testing and evaluation of the performance of devices for electrocatalytic CO2 reduction. And through the exploitation results analysis, we defined 13 results and 4 sub-results that are divided in 11 market-oriented results, 3 scientific, and 1 social knowledge. We also submitted 2 patents, and we foreseen to apply for 2 more patents in the mid-term. And as a words of conclusion, I would like to show you a final video promotional video of SunCoChem.
The European chemical industry strongly depends on carbon feedstock imports for energy and chemical manufacturing processes, standing as one of the largest greenhouse gas emitters in Europe, with over 30 gigatons of CO2 emitted yearly. This demonstrates why sustainable chemistry is more important than ever. To increase the sustainability of the chemical sector, the SunCoChem project has designed and developed a process integrating a modular photoelectrocatalytic device to produce high-value chemical oxo products based on CO2 and renewable solar energy. Following the CO2 capture and conversion architecture, the SunCoChem prototype is divided in 4 processes. Firstly, a membrane is used to separate the CO2 from the flue gas emitted by the chemical industry. Then, syngas, that is CO and H2, is produced in the photoelectrocatalytic reactor. The purified CO2 is reduced to CO, while hydrogen is formed from protons. Simultaneously, the water is converted to oxygen with the use of sun energy. The last process is hydroformylation, in which obtained syngas composed of H2 and CO reacts with chemical precursors. And finally, oxo products, such as limixol or valoraldehyde, are obtained, all to reduce costs and CO2 emissions, moving to a greener and more sustainable chemical industry. SunCoChem, carbon-neutral production of energy and high-value chemicals.
Okay, thank you very much for your attention.
Thank you. Thank you, Adriana. Okay, now I invite the presenters to the table. So if you have questions, if there are questions from the attendees, this is a good moment. Says in the presence of Adriana and Julio.
I have one question. From your point of view, which is the main difference between the photoelectrocatalysis and the PV couplet with electrocatalysis?
I think it's not clear to me if there is an advantage to have everything integrated in one electrode. Maybe, I mean, price, processability, no production. In principle, could be easy if you spray just in an electrode, you spray the semiconductor and the catalyst on the top and so on. The problem is that so far it's really difficult to have something that is stable enough, especially in the part of the semiconductor. So we need basic science in order to solve this problem. Yeah, efficiency could come because you are coupling all the process together. But to me, in the end, it's like there is no much difference if you have a photovoltaic and then a cable and then an electrolyzer. Formally, basically, it's very similar, right? The main difference is the temperature. So when you irradiate directly the sun where you have your catalyst, you are heating up your catalyst. And this could make a difference. Okay, to me, processability and then the factor that you don't have in the photovoltaic unless you couple them somehow. Okay.
Bart? Yes.
Thank you for the talk, Bart van der Bos from Avantium. I like the robot. It's very nice. But you have a full cell, which has an anode, a membrane, and a cathode.
Yes.
And then the robot replaces the cathode.
Yes.
How are you sure that if you see worse performance, that it's not your membrane or your anode that's degrading? Or could you have a robot that also replaces everything?
We can replace everything, but we wanted to start with something simple. So then in the cell is a typical flow cell, okay, and that this configuration is important. It has a reason because we are closer to industry first, and we are gonna form enough material for the analytics. Okay, this is the two roles. That's important to have large surfaces. Then, regardless why we want only to change the cathode, and how we are sure that, well, we cannot be 100% sure, okay, about the performance of the anode and the membrane. What we are planning is to put a very robust chunk of nickel that we don't care how really performs because our reference is going to be in the cathode. It's going to be in this chamber. So in the end, what we're going to see is the overpotential that rise just close to the electrode. And we plan at the beginning to change, once in a while, the anode and the membrane. Let's say 2 days operation. But we need to learn. We need to learn about that. And the membrane, maybe we are not using membranes. Maybe we are using something else.
Because you also said that this is a method to look for stable catalysts.
Yes.
How long do you think you can run for a single run, a catalyst?
I think there is no problem because this is a flow cell. This is a flow cell with the 2 reservoirs, with a peristaltic pump.
So until the catalyst is
dead. Yeah.
Okay.
I mean, as you can imagine, you don't want to have the robot working for 1,000 hours, right? At the beginning, what you want to do is like to screen quickly the catalyst, put some thresholds, then you pick up the best ones, and then you continue another type of phase of a study, and then another phase. Fast degradation tests, maybe this is what you want to do, no, in order to accelerate the process. I don't know. That's something that, I mean, the methodology, how we should work with these systems is not yet clear. But yeah, but it's going to be cool.
Okay, thank you.
Eric.
Eric Schuler, also from Avantium. I also like the robot. I was just curious because if you test a catalyst, usually stability is the problem. So my first part would be, do you develop protocols to accelerate the degradation of the catalyst? And the second part would be, if it's just changing the cathode and you do it every 2 days, we're talking about thousands of hour long-term stability. Did you calculate what the cost difference between a lab technician and a robot arm is?
Yes. I mean, first is about the cost, or about the speed that you can gain with those type of automatization. As I said, so at the beginning, you will not run 2 days reaction with those systems. Probably you want to run 2 hours reaction, okay, until you find your heat, okay, then probably you need to move to another phase of a study for stability, no? Like, I have my champions, then I'm going to take my champions, and then I'm studying in the robot, or maybe somewhere else. So this allows you to really screen really fast systems until you find your champions. Second, so what you are seeing is one cell, but you can parallelize. There is no limitation to have 2-3 cells together working together, okay? The cost of a robot like that, only the cell, I don't think it's going to be much more than a technician 1 year. So I think it will pay very quickly. Then what it was, yeah, I think this is, I don't know if I solved your question already.
The accelerated lifetime stats.
Oh, yes, the protocols. Yeah, I mean, how we started is with the ones that for OER, no? Like fast cycles, positive, negative, and to see where it dies. That could be heating up, maybe. Yeah. High current densities. Yeah.
Thanks.
So thank you for your presentation, Angelica Chiodoni from IIT. So you have the automatization for the testing, but you have the manual preparation of the cathodes, right? Or you have a single-step process. So to plan the experiment, you need a lot of preparation steps to have several cathodes ready to be used, and you have to store them. I don't know how much time they are stored, and maybe they can maybe they are stored in a, I don't know, special chamber to preserve their initial state. So how this is planned?
Yeah. As I say, at the beginning, we want to make our life simple, so preparation is going to be manual, but the process is fast. So that means that, and it can be automatized very easily, because in the end, it's just spray coating, heating up in an oven 180 to 100, 300 degrees maximum for a few minutes, and then you have it. Okay, so in principle, I don't see the reason why we should not be able to automatize this part, but it was not the critical one, so then we focus on the other. Then, this is a good question about the stability. That's a good question. That's a question even that arises when companies that they are making electrodes, they ship the electrodes for making the electrolyzer, the alkaline electrolyzer. That then they realize that they ship the samples and then the electrodes, and then 6 months later, 1 year, they build the stack, and then it doesn't work like it should be, okay? This is a big issue. I guess this is going to be solved or minimized if we synthesize the sample and we test it. But maybe what we want also is to test the stability during time, also in air atmosphere, and then to go for those systems that are stable. I mean, I don't know, maybe we need also to explore this, no? Stabilities in these conditions. Yes. Maybe if something is not stable in air, maybe we don't want it, no? For academic purposes, yes, but maybe for going further, maybe not.
Good morning, Simelis Hernandez from Politecnico di Torino. I'd like to ask to Adriana regarding since you mentioned that this is the very first example of so big photoelectrolyzer for photoelectrocatalytic system for CO2 conversion. Can you comment on what, in your opinion, have been the more challenging parts of this project? So what were the biggest challenge to arrive to this result?
Okay, thank you, Simeris, for the question. In my opinion, the biggest challenge was in the scale-up of the materials, because we started from the synthesis of the catalyst in milligrams, and also synthesis of the polymers in grams, and then we tested them and we moved to the big single cell of 1 square centimeters, and then we had to even scale up more the preparation of the components, and it's very hard to obtain components that are defect-free. And another point was also the reactor itself, that it was very big and very challenging. Even to mount it, we spent a few days to mount the entire reactor, and then you notice that you are missing one thing, or that the gasket is not perfectly placed, and you had to start over. The part of the reactor development in the part of the flow distributors, it was also very challenging, because we had to cooperate, and it was also the exchange of the information in between the people that is developing the material and the people that is testing it. Yeah.
Thank you.
Okay. Any other question from the audience? I think there are not online questions, no, Miriam, because I'm not reading them. I will go for a coffee. What do you think? I think that people agree, yes. So we can start our coffee break before. Therefore, we can start the first session before, 10 minutes before, and then compensate the delays that may occur during the day. Yeah? Okay, thank you. See you in 30 minutes.
Welcome everybody again, and thank you for being here. After the coffee break, we are ready to start the technical presentations to know the main results of the SunCoChem project. So a quick reminder is that for the online audience, remember that you can write the questions in the chat, and for the people in presence, you can raise your hand at the end of the session to ask of our speakers. So let's greet our first speaker. She's Adriana Nogalska. She has a PhD cum laude in nanoscience, materials, and chemical engineering from the URB Spain. She has expertise in electrical engineering, and this allows her to be the head of hydrogen technologies here at the EURECAT chemical unit, and she is the SunCoChem scientific coordinator. The presentation is selective polysulfone membrane for CO2 capturing. Thank you, Adriana.
Thank you. This time I will talk to you about the membranes that we developed in the project. Those are selective polysulfone membranes for CO2 capture. I already stressed out the need for the capture of CO2. There are 4 ways to do that. We can pass by the absorption into liquid sorbents. It's most commonly used technology. It's using amine-based liquids, which are very effective, but at the same time they are corrosive and toxic. We can also use physical adsorption into solid sorbents. They are usually inorganic particles. Membranes, which we will focus on today, and cryogenic CO2 conversion into its stable form by decrease of the temperature. Okay, membrane, it's a semi-permeable barrier that allows a specific species to pass through while retaining the others. And for this separation to occur, we need to apply external driving force. It can be or difference in pressure in between the two faces of the membrane, or different in temperature, or difference in the concentration of the species that we want to separate. This technology is used very often in comparison to the distillation, for example, because of its energy efficiency, modularity, and a small footprint. The membrane technology can be applied in many fields, from the desalination, the water remediation, the gas separation that I mentioned before, also in fuel cells or electrolyzers. In SunCoChem, we were developing membranes for selective CO2 capture in order to obtain a concentrated CO2 stream from a gas mixture that is emitted by down, to obtain the concentrated mixture that can be further used in the photoelectrochemical cell for the reduction. For this purpose, we introduced ionic liquids into a polymer in order to increase the affinity of the membrane towards the permeability of CO2. For the material selection, we based ourselves on our pre-existing expertise and a patented technology that was using polysulfone. It's a polymer that is chemically stable and also thermally stable, and it's very easy to tune the internal morphology of the membrane using polysulfone by controlling different parameters of the membrane preparation. As I mentioned before, we also introduced ionic liquids in order to increase the affinity of the membrane to CO2. The ionic liquids have high CO2 solubility, selectivity, they have low vapor pressure, and also high chemical and thermal stability. The ionic liquids were incorporated in two ways. Firstly, we introduced them to the polymer through a covalent bonding. This was a two-step synthesis where we started from the chloromethyration of polysulfone, and then we passed to the functionalization with an imidazolium pendant. We chose 4 different pendants in order to obtain 4 different polymers. The membrane was prepared by a solvent evaporation technique. In this technique, we prepare a polymeric solution, then we cast it on a support. In our case, it was a glass surface, and we leave it for the evaporation under fume hood in order to obtain a continuous film and a solid membrane. In the polymeric solution, we introduced the polymer that we used, that was unmodified, it was polysulfone. It increased the mechanical stability of the membrane. We dissolved it in an organic solvent. Then we also added the polyionic liquids previously synthesized. And we also added a free ionic liquid in order to even more increase the affinity of the membrane. Depending on the composition of the polymeric solution, we obtained different, maybe I can use the pointer. We obtained different internal structures of the membranes. When we used only polysulfone dissolved in the organic solvent, we obtain a dense membrane. Once we introduce the free ionic liquid just physically, it's inducing a formation of pores. Then through further incorporation of the modified polysulfone, we obtain amorphous and asymmetric internal structure. These membranes were tested for the CO2 capture in a dynamic vapor sorption instrument, where basically we hang our sample in the chamber, we charge it with gas at a specific pressure and temperature, and we measure the change of the mass of the membrane. Those are the results obtained from the testing. As you can see, the CO2 solubility increased once we introduced physically ionic liquids in a comparison to a blank polysulfone membrane. And then each addition of a new polymer that was modified with ionic liquids, it increased even more the solubility. In the case of the permeability measurements, we saw that the simple incorporation physically of ionic liquids slightly decrease the permeability in comparison to a blank polysulfone membrane, which is probably connected to increased thickness of the membrane. However, again, each further addition of the modified polymer increased the permeability. The CO2 and nitrogen selectivity was calculated based on the permeability values for CO2 and nitrogen. And again, we saw the increased selectivity values for all the membranes that were containing modified polymers. With these results, we were able to apply for a European patent in between Eurecat, IIT, and Iolitech on the membranes with ionic liquids for CO2 capture and devices for gas separation comprising them. As a word of conclusions, as we saw that the incorporation of ionic liquid works for our application, we then check what is the carbon capture and storage market size, and we saw that there are provisions that it will be increasing during the next 10 years by 7 times. We are also thinking about our possible end users, which will be not only the industries that are emitting a lot of CO2, which is energy sector, construction sector, or transportation, but also the sectors that need the pure CO2 for the synthesis, which is the chemical industry or beverage preparation. And that's it from my side about the membranes. Thank you very much.
Okay, let's welcome our second speaker. She's Simelis Hernandez. She is an associate professor at the Politecnico di Torino in Italy. In the research group, she leads the research activities related to novel photoelectrocatalytic processes for the sustainable production of chemicals and fuels, where she has been the technical coordinator of several European projects, and between them we have SunCoChem. Her presentation is related to the development and optimization of electrodes and operating conditions for the conversion of CO2 to syngas. Welcome, Simelis.
Thank you, Imar. So I am very glad and very happy to be here today, and very happy to be realized these 4 years of SunCoChem project that with Miriam we wrote some years ago. And today I like to present to you the main achievements that we have obtained in this journey of developing and optimizing electrodes for the SunCoChem projects. I am located, my research team is located in Turin, north of Italy, Politecnico di Torino. Here you have a picture of one of our meetings there. And we are actually working in the engineering school. Here in below you can see the architecture school of Politecnico di Torino. It's a very old university, more than 100 years of history. And in my team at the CREST group, at the Department of Applied Science and Technology, we are developing through a multidisciplinary approach electrochemical and photoelectrochemical processes for converting CO2, trying to engineer in not only the catalyst but also the preparation of electrodes, the design of the reactors, different kind of reactor configurations, and the operative conditions in order to enhance the performance and stability, but always looking at the scalability of the processes. So that is our main target. And in particular, in the SunCoChem project, as also Adriana just mentioned, our aim was to do process intensification by coupling the CO2 capture with the electrochemical and photoelectrochemical CO2 conversion. And in the project, we were able to develop and demonstrate the integrated CO2 capture or separation and conversion together with the development of a scalable catalysts and electrodes that in particular for the CO2 reduction part were based on copper oxide, tin oxide with some organometallic rhenium-based complex, aim to convert CO2 to syngas that is a mixture of carbon monoxide and hydrogen. And this is because, as you have seen and you will see in the next presentation, our goal is to do hydroformylation with this syngas mixture. And so the target was to obtain a syngas mixture of around CO2 hydrogen 1:1 ratio. So looking at our main photoelectrochemical reactor, the reactions that we are willing to perform here are at the cathode, the CO2 reduction to CO, to carbon monoxide, and obviously since we have protons coming from our bipolar membrane, we utilize those protons either for the CO2 reduction but also for the production of hydrogen. On the other side, in the photoanode, that is the sun-driven element of one of the sun-driven elements of our reactor, we exploited a bismuth-vanadate photoanode for performing the water splitting process and the hydrogen and the oxygen evolution. So the materials that we developed was a copper-based electrode for the cathode and a bismuth-vanadate photoanode, and we started our research trying to explore the potentialities of ionic liquids for enhancing the solubility of the CO2 in the electrolyte, and in that way being able to concentrate the CO2 in the liquid media and have a higher availability of our reagent in the surface of the electrode to produce and enhance the evolution of the CO, carbon monoxide. In a first study, we identified that the bimine triflate is a very good candidate of ionic liquid for promoting selectivity towards CO and co-catalyzing this reaction, other than having a good solubility of the CO2. And therefore, we started investigating that ionic liquid. At the same time, we develop a standardized and automatized procedure using spray coating for the preparation of the electrodes. Here you can see the details of the catalyst that was developed in collaboration with other partners. So we prepare nanocubes of copper oxide with copper plus has oxidation state that was stabilized by a shell of tin oxide, and then with some VUTES functionalization, we were able to anchor some rhenium complexes in the surface of the catalyst. And through this technique that was scaled up by Laurencia up to some scale of close to kilograms, we were able to develop a very selective catalyst not containing noble metals for syngas production. So the results that we obtained in this long path trying to look for a better system, better catalyst, starting with ionic liquids, we observed that using these gas diffusion electrodes that were based in a carbon-based gas diffusion layer, we obtained some instabilities after some time regarding the production of the CO and an increase of the evolution of the hydrogen. So we identified what were the issues related to these phenomena with some molecular dynamic simulations, and we observed that actually this organic solvent that we were using, that was acetonitrile, basically displaced the copper atoms for the surface of the electrode, and then we have a very good affinity with the triflate anions that were in the solution that basically dissolve the copper surface, dissolving the copper species in the electrolyte. And other than that, the exposure of the carbon-based support also affected this gas diffusion layer, damaging the support and creating some amorphization of the carbon material and some hydrophobicity loss of the electrode. So these were the reason of this instability on the material. So for that reason, and to go ahead with the goals of the project of demonstrating a high scale syngas production, we decided to shift towards the utilization of aqueous-based electrolyte, but in this case, to tackle the problems of a few solubility of the CO2 in the water media, we decided to use a gas diffusion electrode configuration that entails the direct feeding of the gaseous CO2 to the backside of our electrode, so to have a good high concentration of CO2 in the surface of the catalyst and allow a good conversion of the CO2 in this kind of system. So we were able actually to demonstrate that our catalyst was very stable for the production of carbon monoxide and was very selective at even at the conditions, target condition of our project that was operating at 20 milliamp per square centimeter. This is a test that we performed for 24 hours in the lab. Also scaled up the process from the laboratory scale of 10 square centimeter to 100 square centimeter scale. That was the TRL3 target of the SunCoChem project. To do that, we scale up the process of screen printing in our labs at Politecnico di Torino for preparing all the electrodes that were also used in the TRL4 and are being used now in the TRL5 demonstrator. And Helmont Centrum Berlin also scaled up the process of preparing the bismuth vanadate photoanodes with a automatic film deposition technique. And in our labs, we tested the TRL3 prototype exploiting these two photoanode and cathode, and we demonstrated actually a very good stability of the system, and we fine-tune the process conditions to be able to obtain the CO2 hydrogen ratio that was required in the project. With those tests and after several optimization of process parameters, catalyst loading, and ink preparation, components in the ink, etc., we were able to achieve a CO2 conversion efficiency of 30%. That is actually one of the targets for achieving industrially relevant application of this technology. And we were able to demonstrate up to 4% of solar to fuel conversion efficiency that could become 4.5% if we use photovoltaic panels, that the ones that will be used in the final demo are being used in the final demonstrator for providing the voltage to the process. So just some highlights about this very challenging process of trying to optimize our electrodes. Here you have some of the main challenges that we face during this development. For example, the poor sunlight utilization of the photoanodes is a very critical point in this kind of research. We, during the project, developed sulfur-doped bismuth vanadate photoanodes to enhance light absorption and reduce recombination of charges, so to have a better performing photoanode, and in this way reduce the overvoltage needed for the reaction. To face the challenge and mitigate the challenge regarding the instability of the catalyst and photocatalyst, we add some co-catalysts to our electrodes, so nickel oxide, for example, in the photoanode, and renew-based molecular catalyst in the cathode. And also we had to use Hall scavengers in the anolyte in order to enhance the kinetics of the process. Regarding the flooding of the electrode, as I just mentioned, this can hinder the selectivity of the process and the CO2 reduction, and actually is one of the problems that we have also during the TRL4 demonstration here in EURECAT. But this can be solved actually, and was solved in the TRL5 prototype, by being able to regulate the pressure in the gas chamber. In that way, we are able to control the differential pressure between the gas chamber and the electrolyte, and in that way be able to recover the CO2 reduction ability. And the last but not least was the dilutant effects, and to do that, we incorporated, to resolve that issue, the separation purification membranes system in order to have a CO2 pure stream that arrive to the photoelectrochemical reactor. There are also other engineering issues that are very important for the real practical application of these kind of processes that we encounter in the project, but will be better explained then by my colleague Freddy Liendo from EasyTech. So thank you for your kind attention, and I will be happy later to answer questions.
Thank you, Simelis. Thank you very much. Let's welcome our next speaker. He is Freddy Liendo. Freddy Liendo obtained his PhD in chemical engineering at Politecnico di Torino in Italy. Right now, he is a research and development specialist and process engineering in EasyTech. Right now, he is involved in several European projects, leading the development of new emerging technologies and processes to tackle climate change, and SunCoChem is one of them. The presentation of Freddy is related to the photoelectrochemical device scale-up and commercialization expectations. So welcome, Freddy, please.
Okay, thank you. Good morning, everybody. Thank you, Ilmar, for the kind introduction. So just she already mentioned, I will be talking about the photoelectrochemical device scale-up and the commercialization expectative. So we'll be sharing what is the motivation, what were the challenges that we had during the prototyping, scale-up, and optimization of the process, as well as the system integration of all the materials and process developed within the project, and what are the expected results and main remarks of the project. So, as we know, so the current situation about CO2, so we are in a record CO2 concentration in the atmosphere higher than 420 ppm. So, and the emissions from the chemical industry are quite high. So the proposal is to have a circular economy or reutilization of the CO2 in integrating the carbon capture, the syngas production through a photoelectrochemical process, and with the hydroformylation and purification of these products that have a very high added value. So us at EasyTech, so we are an engineering company that, as my colleague Ilmar mentioned, we are involved in several projects. So our main role in the different projects are the prototyping of several technologies. In this case of SunCoChem, we are, let's say, concentrated in the scale up from TRL 2 to TRL 5. So in which we started from the outcome from the laboratory of our colleagues in the Polytechnic of Turin, EURECAT, and HCB for the electroreduction of the CO2, as well as the hydroformylation and purification of the process, and also for the CO2 capture. So then we passed to a TRL3 system in which we increase the, let's say, the size of our prototype by 10. So and this was also tested in their premises. Then we pass to a TRL4 in which we just demonstrated the CO2 electroreduction to syngas, and the results were also the results from this were also used for the hydroformylation steps by our colleagues. And then we are developed an integrated system in which we have all the process in one system, and it's installed now in Tarragona, as you can see here in the picture. So the principles that we follow for the scale-up of the photoelectrochemical reactor is to try to bring the same, let's say, process similitudinous of the system from the lab to the real scale process. So electrical connection with minimal parasitic power losses, distribution of the reactor over the electrode surface, so we can have a homogeneous process among the entire reactor. So for this, it's important to have a very fluid dynamic distribution, low pressure draft between inlet and outlet for each one, membrane hydration, and so these are the principles that we have followed so far for this. So for the scale-up and optimization, we first, as I said, fluid dynamics, homogeneity, pressure drops, then the process integration for the 4 processes, taking into account always the scope or the goal to reduce capex and opex that could allow us to demonstrate that our technology will be also economically feasible. And then there is the process validation for the testing and optimization of the final details and the process assessment to assess the yields and also the quality of the product that we have with the collaboration of IFF that it's helping us for this final step. So for the first scale-up that we had, so the TRL3 prototype that we manufactured, what we did, we exchanged information with our colleagues from Polytechnic of Turin and HCV. So we tried to replicate what they had in a small device. Then so we optimize or try to optimize the fluid distribution among the entire electrode surface. We also verified the compatibility of the materials that we were implementing to work under sun and high temperatures. And that a material and the design that could resist deformation because of pressure, or also because only for the closure of the device. Then for the these are the main results that were already shared by Professor Hernandez regarding the process, the test at TRL3, in which we had up to 30% of conversion of CO2 towards CO, so and having a mixture of syngas equal to 1.5. That this mixture was also let's say replicated in the laboratory by EUROCAT to testing also the hydroformation reaction, and under this so it was proven that under these conditions also the hydroformation could work, giving good results in terms of conversion and selectivity. The same was done then for the TRL4 prototype, so we passed from 1 cell to 20 cells that were distributed in 4 strings of each 5 cells each, with the integration of the PV panels for feeding also the electricity to the device. And in this case also we obtained very interesting results and maintaining the same ratio of in this case the ratio of H2 to CO was changed. Anyhow, this was also tested in laboratory for hydroformation reaction, and there was not important, let's say, changes in the selectivity and the conversion of the raw material towards the oxo products. There were some challenges and, let's say, drawbacks that were encountered during our TRL4 testing that were mainly related to how the flow was distributed among the different cells in each string, but also among the different strings. So we started from this design. Then we saw that there was like the main problem was attributed with the pressure difference and how the flow was distributed because of this. So we made different iterations and using CFD simulations, we arrived to a final design in which we mainly increase the width of the manifold that allows an homogeneous distribution of the flow and reduce the pressure drops in it. So and it was also tested before constructing and obtaining interesting results with very interesting flow distribution that was homogeneous, and now it's installed and at Amposta for the validation campaign. So the approach is the integration for the final integration, so that in which we have the flue gas from the chemical industry that is then captured using the membranes developed by Eurecat, the syngas production through the photoelectrochemical system that was developed, and hydroformylation and also and the purification. So we have 4 different units, in which the first one is here represented, in which we have this is the project in which we have the feeding of the flue gas. By pressure difference, the CO2 is separated, exploiting also the selectivity that this membrane have, and so you can see how it passed from the project modeling to the reality, and that is what we have now in Amposta. The purified CO2 is then fed to the photoelectrochemical reactor to produce gas. In order to increase the composition of gas, so we implemented a recirculation loop using a storage tank. In this case, it's a balloon. So it's reused to recirculate CO2 and increase the composition of gas to have enough, let's say, syngas composition and increase the overall yield of the process to be implemented then in the hydroformylation reaction. The hydroformylation reaction is carried out by feeding our mixture of syngas. It's before compressed using a compressor's battery that allows us then to operate the hydroformylation reaction at high pressure and controlled temperature according to the operating conditions that were shared by their colleagues, and also with the collaboration with the IFF, all these steps were also verified. And then finally we have the distillation, that is the process that was selected for the purification of the system. So this is just a batch distillation in which we just separate raw material from the final product. That is the limoxal. That is the mode that we are now running. Then this is also the system is also possible to the electrical cabinet and that we have, so the electricity feeding and the control system that was developed. And so the overall expected results of the TRL testing campaign that we are now running is to have a CO2 electron reduction using sunlight with a productivity of 2.6 kilograms of limoxal with high purity, so demonstrating a carbon capture and utilization technology by exploiting renewable energies, meaning in a low carbon footprint limoxal production. The main remarks from this presentation. So it was a challenge to have the scale up of the reactor, but with the hard work during these last years, it was possible. So we were able to integrate the carbon capture with the same gas and limoxal production. The prototype testing campaign is demonstrating an eco-friendly pathway to produce OXO products with competitive price. This will also be then discussed in the next section with the techno-economic analysis. And the materials development and process optimization is still needed to increase economic feasibility, but this is, let's say, part of research. This will be also discussed later. So the SunCoChem prototype installed and running on POSA is demonstrating the photoelectric reduction CO2 integrated with hydroformylation for the first time in history at TRL 5. So this is all from my side. Thank you.
Thank you very much, Freddy. Okay, let's invite our final speaker of this session. He is Bojan Iliev. That's correct. Bojan is the head of custom synthesis of Iolited company. Bojan obtained his PhD degree in organic chemistry at the University of Zurich, and his postdoc experience from University in Stuttgart. With more than 15 years of experience in synthesis and purification of ionic liquids. Today, he will talk to us about CO2 capture with ionic liquids, a reality or a dream. Let's see. Welcome.
Thank you very much. So, let me just get some water because I've got a small cold, which I hope will not interfere too much. But I would like really to talk to you about something that we've been developing not only within that project, but also a few other projects that I'll allow myself to mention within this presentation. And the question is, indeed, there are quite a lot of papers on CO2 capture with lots of things, among which, of course, ionic liquids. The question is, to what extent is that extendable to a viable industrial process? And this is what I'll try to go into, of course, as part of the SunCoChem project. A short introduction on what ionic liquids are and why you want to use them for CO2 capture. Moving on then to some industrial applications, including direct air capture. It was something which was mentioned by our plenary speaker in the morning today. Then move on to CO2 conversion and utilization. Then I'll end up with a short summary and a few words about our company. For the ones of you that are not familiar with the concept of the ionic liquids, this is a relatively new, well, relative of course, they've been on the market for the past 20 years or so. So 40 is the new 20, okay? But anyway, it's a class of materials that are completely ionic, which means composed only of cations and anions. And by choosing them wisely, you can actually force those materials to be liquid at even room temperature or below. Why does that happen? If you compare to, let's say, a standard sodium chloride, which you can see somewhere here, you have completely symmetrical cations and anions. You have almost no charge delocalization. As a result, the forces that bind them are relatively strong, which means you need a lot of energy to get them apart, which means to get them liquid. What we do is use organic cations, also trying to delocalize the charge both in the cation and the ion. As you can see here, a major part of this is the symmetry in your system, and then, as I just said, the delocalization. For the specific case of SunCoChem, when, as you heard already from 2 presentations, we ended up making a membrane for the CO2 separation. You don't really care about viscosity because, I mean, you have a membrane. But if you want to go to a, let's say, liquid scrubbing process, then of course viscosity is a problem because of mass transfer numbers, kinetics, so on and so forth. So this is an important issue. Why would you want to do that at all? What's the benefit of ionic liquids compared to, let's say, state-of-the-art alcohol amines? I mean, there's a list which is probably not complete, but I would say the most important part here is, yes, of course, you can reach higher absorption rates, faster kinetics, whatever. But as you can imagine, for us scientists, those are the more important parameters. For people from the industry, I'm sort of like sitting in between, I guess. The question is the cost. And the main benefit of using ionic liquids for CO2 capture, no matter how you do it, is, well, at least in a scrubber, is that you have very much reduced energy costs for both for the capture and for the regeneration. And this is, at the end of the day, what gives you your, let's say, financial push in order to, or what gives you the advantage over the standard technology. You have, of course, lots of different options. Sorry. Based on what kind of flue gas you have, if you want to regenerate with pressure or with temperature, if you want to do physical sorption, chemical sorption. Lots of different possibilities for each of them. There seems to be a solution somewhere there. Or you can, of course, do what we did within SunCoChem, that is use a membrane, which, as you saw already today in the morning, Adriana showed very nicely, works like a charm. And we have a patent running on that application. As I said, the optimal ionic liquid is, at the end of the day, a function of your flue gas composition. So for almost every type of flue gas available in industry, you can find some kind of, ionic liquid that will actually fit the job. In the Dow flue gas composition that we planned to use in the project, we would have been somewhere between those two, I guess. And we had quite a lot of possibilities when it comes to ionic liquids in order to be able to make a viable process. But as Simele said, we had some problems with the stability of one of the catalysts and the electrode, so we switched to an alternative solution. What's probably important at this stage is to say that in most cases the oxygen content is probably the most unpleasant contaminant in your flue gas, because this limits you the most in the choice of ionic liquids, which doesn't mean that you cannot find a solution. It just means that the most active chemical sorbents are, as you can guess, amine based, or ionic liquid amine based, put it whatever you want, but generally, this is something you cannot use in that case. Just a small example of another project that we did with, well, most of you actually. It's the Recode project, but just to make it short, yes, there are pilot plants running on TRL 5 level, which show that CO2 capture with ionic liquids is possible. Different flue gas composition, different flue gas sources, different flow rates, as you can see, and efficiencies going up to 95-ish% on a good day, like sunny like today. And when there's no power shortages as we had in the morning. But in such cases, this actually works pretty well. So going on to SunCoChem and the ionic liquids that we use there, the main idea at the beginning of the project was to have one single ionic liquid that will, kill them all. So basically use it both for CO2 capture, for the CO2 reduction, and the hydroformylation process. As most things in life, this was too good to be true. And we ended up having to split, But anyway, on the right here, you see this bimim succinimidate. This, after we found out that we will not be able to do the reaction within the ionic liquid, said, okay, so those restrictions that you can see here on the left, especially last point, the not strong nucleophiles, that will then, of course, be a problem in your hydroformylation process. We're not really valid anymore. We said, okay, we'll take something which is really chemically active and has a very high CO2 solubility with this. You can see here on the right this bimim succinimidate. The other two marked in green are the ones that Simelis did more stuff for experiments with. And there are some pretty nice results, if you ask me. At least I'm a big fan. Anyway, of course you need to produce those on a larger scale in order to be able to make a proof of concept, Sorry, it's just not making like 10, 20 grams. That's easy. The question is, if you want to prove an industrial process, you need to be able to do that on a large scale as well. So we're talking like hundreds of kilos or even more. What would a normal chemist do? Take a small flask, then take a bigger flask, then if you need, like, take a bigger reactor, The catch there is that if something goes wrong, you have a big mess, like a very big mess. The very nice things about flow technology is that what you're doing is you're basically mixing your starting materials, you're passing them through a, let's say, reaction chamber, or in our case, this was really relatively easy, a tube. And then you have your product. So you don't need solvents. You can very nicely control your reaction conditions because you have very good pressure and temperature control. Because it's one thing mixing up, a 1-ton reactor. It's another thing to have mixing in a, thin tube. And the product really comes like really, really nice and really, really clean at the end of the day. And with that, we were able to produce the precursors for the above-mentioned ionic liquid on a range of, let's say, 25 kilos per day on a single line. So if you need a ton, you just make 4 lines, you have in a week, and you're done. So this is actually a really nice way of scaling up ionic liquids production. The really nice thing I mentioned just a few minutes ago about the results from the Polytechnico is that depending on the ionic liquid or the ionic liquid composition in your mixture, you can very nicely and very finely tune the composition of your syngas or what you're producing. As you can see here from the left, from almost pure CO to the right to almost, well, the other way around, of course, almost pure hydrogen to almost pure CO. And anything in between. So this is a very easy, very versatile method of fine-tuning your gas composition. And of course, as you can imagine, both the cation and the ion have an influence on the whole process. Sorry, this is, you can see why we took the BIMIM instead of the IMIM, which is like the standard from literature. You can see on the lower right, the BF4 is the standard, again, from literature. We're able to surpass that with the triflate quite nicely, both in terms of electrochemical stability and of course, of performance. So, to sum it up shortly, sorry. Ionic liquids can capture CO2 both chemically and physically. And we have seen today that the so-captured CO2 can be very nicely used in an electrochemical or photochemical reaction to produce high value-added chemicals. The choice of ionic liquid depends, of course, on the composition of your flue gas. I'm really sorry about that. And a question which will come, I'm sure, is the price of the whole thing. prices of ionic liquids are a major factor and will be a major factor. I will be lying to you if I tell you that ionic liquids will cost someday as much as like toluene or something. This will most probably not be the case. But still, the prices will follow the economy of scale, and we have some calculations that I was not able to show you today, but they show that this process is economically viable. So, a few words about the company. Yolitech since 2003 on the market, so more than 20 years. We do, as you can guess, ionic liquids, and we're at this moment 26 people. We have a big production site in the eastern part of Germany, and with that, I would like to finish, and thank you so very much for your kind attention.
Okay, thank you very much, Bojan. I invite all the speakers, please, to come here to the table. Take a seat. Okay, we will start now the questions and answers session. So, do you have any questions for the speaker? Yes, please.
Okay, thank you. Thank you, very interesting. I have a question for Ximeli Hernandez about the enhancement of the increasing of the band gap, because you said that then one of the challenges, of course, is using sun energy. So how you told something about nickel, but if you could develop a little more, how to increase the band gap of the bismuth-vanadate?
Yeah. This was a work that was done by the colleagues at the Helmont Center in Berlin. And what they did was to try to enhance the band gap of bismuth-vanadate by doing sulfur doping. Actually, during the project, also in collaboration with Eureka, were studied the organometallic complex to has light absorbers, to be able to try to enhance also the absorption of sunlight, the visible part of the sunlight that's not absorbed by bismuth-vanadate. But at the end, due to some processing issues, based on the fact that bismuth-vanadate needs to be annealed at very high temperatures, while the organometallic complex cannot be stable at those high processing conditions. So due to these issues, at the end, the organometallic complex that could work for enhancing band gap was not possible to use at the end in the final demonstration of the project. But yeah, what was done then was exploring a more inorganic procedure to do this sulfur doping, and this indeed enhance a bit the window of absorption of the light, of visible light. And the nickel oxide was used for co-catalyzing the oxygen evolution process and enhancing then the kinetics of the oxygen evolution reaction.
Okay, thank you very much.
You're welcome.
Really interesting and a lot of work done. I have a question about the flue gas treatment and the integration of the CO2 membrane. So first I was wondering whether you tested a membrane also with the flue gas composition from Dow, and whether you then solved the oxygen problems you elaborated on, Similis. And when I wanted to know, you integrated it in this process, but now in the final prototype at the TRL5 one, it's external. Can you elaborate on the decision why you took the membranes out of the integrated design?
You don't have the microphone.
right in front.
Okay, thank you, Eric, for the question. Initially we were testing membranes with the pure CO2 and the pure nitrogen. There are also some tests that were run in a flow cell with a different concentration of different species. In the final pilot, we are going to use a simulated gas outcome from Dow, which will first pass through the separation stage with the membranes, and then purified CO2 will be fed to the electrochemical chamber. You also asked why we decided to split. So initially we were also thinking about preparing a membrane electrode assembly using the bipolar membranes. Then we would have the bipolar membrane, the electrodes, electrolyte, and the membrane to separate CO2, which means that this membrane would have to work with the gas and the liquid. Okay, but at the end we saw that it was very, very challenging to obtain a membrane electrode assembly. It was very hard to introduce the catalyst on the bipolar membrane surface. So we decided to go for the flow cell, where the electrodes and the membrane is separated, and the same the gas separating membranes was then used to separate the gas in the gas-gas system. Thanks.
Yeah, hello. I want to thank all of the speakers for their quick but detailed overview of the project today. I have a question for Dr. Angelica Chiodoni. So, as you have heard, at Polito we explored the effect of CO2 dilution, no? So, following up the question from Eric, we have preliminary results that show that that dilution, CO2 dilution, have an impact on the selectivity, but also on the morphology. We did some ex situ measurement, ex situ characterization of the electrodes. So my question for you is: do you think might be possible to simulate, so to change the concentration of CO2 in for your TEM operando characterization, and how do you think that this can also impact the results that you showed today? Thank you.
Thank you for the question. So yes, it's totally feasible. It's let's say an experiment in which we have to take the electrolyte with a different saturation, and in principle we have the capability of make the mix or select two. We have two liquid channels, so we can push the liquid saturated with the CO2 and then make the switch to a electrolyte saturated with nitrogen. Of course, if you do this contemporarily, we see the changes that are the changes that are depending on the experimental conditions. So if we start with this with the CO2, and we saw there are some effects by electrocatalytic behavior of the catalyst. If we change the saturation, probably we will see what would be maybe the weak points, if any, on the initial catalyst, and see the evolution of whatever precipitate or for new crystals formed. So it is feasible. And as I say, we can also consider a mixing of the liquids if we have two liquid lines. So we can increase the saturation with nitrogen with respect to the CO2 or the contrary, and see what happens. We cannot start from the beginning. At that point, we have to have that initial state that is not really the initial one, but we can follow what is happening. Yes.
Okay. Thank you.
Okay. First of all, thank you for your very interesting presentation, all of you. I have two questions, one from Hernandez. I'm wondering, like, what is the stability of the membrane functionalized by ionic liquid when we use water in the system for both physically incorporated ionic liquid and the other one?
Yeah, regarding the membranes, I will ask Adriana perhaps to answer. Sorry.
You need to pass me the
Yeah.
micro.
Yeah, okay. And just the
The
other
second
question from Boyan, I wanted to know, is a general question, how far you see that the ionic liquid would be implanted in the CO2 capture in a big industry, and for the moment, do you have any idea how many pilot plants are running based on an ionic liquid for CO2 capture? Thank you.
Thank you very much for your question. So basically, this is why we did the chemical incorporation of the ionic liquids in order to induce the stability of the membrane, because it's known if you incorporate them physically and if they are soluble in water and you use a membrane with the aqueous solvents, then there is a leakage of ionic liquids. So the chemical incorporation improves the stability of the membrane. However, the physical incorporation is still increases the affinity of the membrane towards CO2. Finally, we are going to use this membrane not using the aqueous absorbent, but we will just use them to separate the gas. So we will have a gas-gas separation. So this issue will be not, well, it will be solved by itself. Okay, thank you.
Oh, I have one. Sorry. Let's put it that way. I believe there is a future in CO2 capture with ionic liquids, but not on a mass scale. So it's at this stage, and for the next 5 to 10 years, it's illusionary to think that such large amounts of ionic liquids will be pushed into the market in order to allow for a price which is low enough. What I see as possible, though, is to have the localized CO2 capturing for niche applications, and especially where the transformation of the so captured CO2 is taking place where the CO2 is captured. So an example of, like in our case here with SunCoChem, the Dow is then producing the CO2, capturing it, transforming it at the same place, and then using it further without the need to store it or transport it. This is the only way that I see feasible that will make the difference and will actually allow for this technology to be more widely introduced into industry. Everything else is too far-fetched and will be just too expensive compared to other currently available alternatives. To your first question on the pilots, to the best of my knowledge, in Europe at least, there is not a single, let's say, pure ionic liquid operational pilot plant. The ones that I mentioned were part of European projects, and after a certain time they have been put to rest. But there are rumors that in China they are doing this on a larger scale. To what extent this is true is unfortunately not clear, at least not for us.
Thank you.
Just to continue with the question, now I have the opportunity. Thank you. So it's related to the fact that, I mean, you are considering to concentrate CO2 from atmosphere, like direct capture, no, for 100 ppm, 120, to basically 1 bar, 100%. So, but what about 10%? Is this feasible? This could make sense because perhaps the pressure on the concentration and transformation could be shared? Let's say, if this makes sense, or is something like come to my mind? I don't know.
Let's put it that way. I'm just the cook, so I'm not an engineer. But I would say yes, it is. That's why I said, I mean, as a general, general purpose tool to put like on every single CO2 emitting industry in the world, this will not work. But for such cases where you can actually share the load, I think this should, or I hope it's feasible.
Thank you.
Thank you. Let's pass to the online questions. Okay, let's pass to the online questions. This is for Sara. Which are the bipolar membrane issues and why incorporate fibers?
Thank you for the question. So the bipolar membrane has the advantage and disadvantage, first of all the monopolar membrane that are composing them. So it depends also on the chemical nature of proton and anion exchange layers. And then merging them, the first issue is a mechanical issue, especially at high current. It can be a delamination of the two layers. So that's why putting this 3D interface layer made of fibers can interlock and so increase the adhesion because it's a 3D interface instead of a 2D interface. So first of all, the mechanical properties, then there are issues with chemical and thermal stability, and this is basically due to the anion exchange layer part. So these are research on chemical synthesis of novel anion exchange layers. And then, as I told you, it is important also to improve the rate of water dissociation in the interface layer. So as I show, the electrospan mat can be used as a scaffold to immobilize and make stable catalyst at this interface. So for this reason, we choose the fibers and the electrospinning also for the versatility, upscale, and what I already said in the presentation.
Thank you very much, Sara.
Thank you.
Okay, the last question is for Freddy, and this is: what are the main changes and improvements done at the final reactor in comparison to the first cell constructed?
Well, thanks for the question. Yeah, the main change of the reactor was related to the how the flow is distributed and how what is for example, not only for the flow distributors, and also have let's say the perfect or adequate width of each chamber, so in order to avoid increasing the ohmic losses and resistance inside the cell, but also guarantee that there is not leakage or anything in the cell. So the changes were more related in the geometry mainly. This is when we pass from one cell to five cell string, and then to integrate for the final prototype in which we had 20 cells. Also, we had to integrate like a pressure control, because in order to maintain the difference, the differential pressure among the different chambers in each cell. So it was a very big challenge, but in the final, we found the way to control it. So, yeah.
Thank you very much, Freddy, and thank you very much for all of you for the nice presentations. And right now we have 10 minutes of break, but this is only to put the microphone and so on for the next speakers. So I ask you please to be here in the room. If you need to go to the toilet or so, you can go, obviously. but please stay here for the next session, that is exploring the societal, economic, and environmental impacts of SunCoChem. Thank you very much.
Thanks.